Today we're going to discuss about architectural modeling. Okay, the concepts under architecture modeling are components, component diagram, deployment diagram. Yesterday we have discussed about components. Today we have to discuss about component diagram. Component diagram. So what is an architectural modeling? In this architectural modeling, we will design the physical architecture of your system. Okay. Now we are going to discuss about component diagram. So component and component diagram. In components, we will discuss about components, all components in detail in UML. But in component diagram, we will discuss about the diagram. The main focus on diagram, how we implement real-time diagram using component diagram. So component diagram, it is one of the architecture modeling. Component diagram, one of the kinds of modeling which models the physical aspects of your system. Using this concept component diagram, it shows organization of various files and also dependencies among these files. The main use of component diagram is to model the static implementation view of the system. If you see this diagram, this is a component diagram. A component may be, as I told you earlier, a component may be a file or a document or a table, database table or .exe file or .html file or .dll file, which is a data link library. All these are components in this diagram. If you see, if you see, index.html is dependent on find.html. This find.html is dependent on this component find.exe. So this component is dependent on these library files on dbasics.dll and neteng.dll. So this component won't execute, is dependent on this file. Without this file, this find.exe cannot be executed. So what are the contents of component diagram? Component diagram contains components, interfaces, dependencies, generalizations, association, and realization relationships. Like in all other diagrams, this component diagram may contains nodes means comments, nodes and constraints or rules. This component diagram contains some constraints which is rules, and also it contains nodes such as comments to describe your diagram. So the common uses of this component diagram are, it is used to model the static implementation of your system. So these are the four main common uses of component diagram: to model source code, it, to model executable releases, to model physical databases, to model adaptable system as well. So first of all, how to model? So these are the common modeling techniques which can be done by component diagram. The first common modeling technique is to model source code. So how to model source code? In order to model source code, first of all we have to identify the source code files. Then we have to model these source code files as components using some stereotypes. For larger system, we use packages instead of instead of source code files. We use packages we represent in the model, and also, so we also use tagged values in the component diagrams for for version number. For tagged value is nothing but it will tell the version number, author name, date. Okay, so how the version number? So we can represent the version number, author name, and date using tagged values. And also, while modeling this source code, we have to model dependencies among these files. If you see, as I told you earlier, first of all, we have to identify the source code files. So these are the source code files we after identifying. If you see, so this for this signal.h 4.1 version, so for this version, the signal.h is the parent, which is version 4.0 is a parent. For version 4.0, Version 3.5 is a parent. So this is the grandparent, this is parent, this is a child. So this signal.h, this is the child. So the files like interpiece.cpp, signal.cpp are on dependent on signal.h, whereas this is inter.cpp dependent on irq.h. So this device.cpp is dependent on inter.cpp. So all these are depending on among themselves to execute a component to model a source code. So next common modeling technique is model executable files. How to model executable files? To model executable files, first of all we have to identify the set of components. After identifying the components, we have to represent these components using some stereotypes. Then what we have to do, we have to consider relationships among those components and to make a executable files components. Okay, so this is a executable, this is an example for executable modeling executables. So if you see, this part.dll is depend on collision.dll library file. DLL means data link library, and also it is dependent on this interface I drive. So this driver.dll, which is a version number 8.1.3.2, is implements two interfaces like interface drive and interface self test. So this is how we model executables, execute files, exe files. Next, it is also next common modeling technique is modeling physical databases. To model physical databases, first of all, we have to identify the classes that represent the local database schema. Then we have to select a strategy for mapping these classes to tables, and we have to represent this component diagram using components by using stereotypes as tables. Then by using some tools, we transform this model into physical design. If you see this is an example for modeling physical design. So this is a database, school database. So this is a composition symbol. This the bolded diamond symbol is a composition symbol, which means this this instructor cannot depend on school database. If there are this is a database. Database contains some tables: course table, department table, instructor table, school table, and student table. So all these in are not dependent, cannot exist independently without this school database. Without school database, these tables cannot be executed. That's why it is a composition notation. So next common modeling technique is modeling adaptable system. To model adaptable system, first of all we have to consider the components that migrate from node to node. So adaptable means adapting from one node to other node. Okay, so so then we have to specify the location of each component by using tagged name is equal to value. Then we can illustrate change the location by taking one instance more than one time with different values. So how can we change the location? By tagged value we can change the location. This is an example for how to model adaptable system. So first of all, there here this there are two databases. One is located at server A, other is located at server B. Using from server A, we are copying the database school database to server B. So this is the school database. This B server is replicating, copying the database from server A. In this way, we can adapt the systems. Forward engineering means making code from model, using model as input and getting output as code. Converting from model to code is a forward engineering. To model forward engineering, first of all, we have to identify the classes and their collaboration among themselves. Then we have to select a target for each component. Then using some tools, we have to do forward engineering for models to get the code. Next, for reverse engineering, first of all, we have to select the target. Then we have to execute source code, binary library. We have to bring from code to model. That is reverse engineering. So how to get the how to get the model from code. So first of all we have to set the target, then we have to take source code, binary libraries, executables as input. Using some tool we can generate from code to new model. So for giving code as an input, and we will get model as an input, model as an output. So this is the reverse engineering. Here this is vBrown.dll is a ActiveX component. This ActiveX component is a technology used by Microsoft. It is used in Windows application, Windows operating system. So this the main use of Active component is to reuse the application without 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 developing from the scratch. Okay, this is a ActiveX component. It implements various interfaces. So this ActiveX component enables software application to use the functionality and save the applications. So that's it. Thank you.